Hi folks, and welcome to another episode of Open Analysis Live. So first off, really sorry about the 5-month hiatus where we put out no videos. It just so happened that at that time I was starting a new role at a new company, and it took all my time to sort of get up to speed. I'm working with some really smart folks right now. And it took a lot of time to try and get up to their level. But in the groove now, and hopefully we will be trying to put out more videos now that we have a little bit more free time. So without further ado, let's get into what we're talking about today, which is patching binaries. So just going to be a really quick tutorial on how to patch a binary, how to locate the bytes that you need to patch out in IDA, and how to patch it in a hex editor, basically, and what that looks like. So pretty simple, but I get asked about this a lot, so I figured I'd make a video. And I'm actually going to use a sample that I patched for a friend of mine a little while back, so that it would run in a sandbox. So that's kind of what we're going to talk about today. And I think what I'd like to do is just kind of show you the sample. So it's a DLL that was decoded. It's part of an infection chain where I think there was like some PowerShell that loaded this as a DLL in memory, and then this DLL went and downloaded the actual payload and executed it. And what he wanted was this DLL to be able to run in a sandbox, so it wasn't running. So here you can see I've pulled this up on hybrid analysis, payload security. They have so many names I can't keep them straight. Anyway, y'all know what I'm talking about, the free online sandbox that everybody uses since Cuckoo started going 500 errors on us. So basically, this is a DLL. It has 2 entry points, as you'll see down here. But you can see here in hybrid analysis, one of the cool things that they do is they will rerun, if it's a DLL that has multiple entry points, they will rerun the DLL in the sandbox, trying each entry point, because a lot of times malware authors will create a DLL that has, say, like 4 entry points. 3 of them are going to be nulled out, fake, and the 4th one is going to actually be where the malware code is loaded. So what hybrid analysis does is they just automatically try all of them, so that basically so that all the bases are covered. So in this case, you can see that there's 2, one called void func and one which is just the DLL main, which is basically no entry point. It's like the ordinal 0, basically. So that where there's actually, you're not calling an entry point. Ordinal 0. Good trivia. If we ever had a reverse engineering trivia night, ordinal 0 would be how you call DLL main. So anyway, we can see here hybrid analysis has tried both of them, and then if we roll down to our traffic, there's no traffic, no contacted hosts. It looks like the sample didn't really run. No extracted files, blah, blah, blah. It looks like something's wrong here. And like I said, my buddy who sent me this file over said the same thing was happening in a sandbox. He got like some API calls and whatnot, but no network traffic. And since he was pretty sure that this was a loader, he wanted to actually pull out the network traffic so he could get some IOCs for it and download the payload. So we can see up here, this is a little bit misleading. So we can see in the images that hybrid analysis has taken, we can see they're using run DLL. They're running it with the void func entry point. But what's a bit misleading is we have this error here saying missing entry DLL main. I think what's happened is hybrid analysis has tried to run the DLL with ordinal 0, and that's caused this error. I could be wrong about that. But when I loaded the DLL into debugger, I certainly didn't have any errors like this. So I think that's probably what I'm going to show you next. Is I'm going to show you what this DLL looks like in IDA. We'll load it up, and then we can basically see the entry points. We can see what's loaded with each entry point, and I'll show you basically what's stopping this DLL from running. It's kind of a clever trick. It's not really the focus of this tutorial. It's not really like what is this DLL doing. It's more about the patching. But I'll just show you anyway so you know what's going on. So if we pop over to our IDA instance here, our Windows VM. So I'm just going to start up IDA here, and I'm going to open up our DLL, test.dll, open it up. Yes, interpret it, please. Okay, so IDA is doing its little analysis thing. It's finished, must be pretty small. So if we look at the exports, you can see We have like the main entry, which is ordinal 0, or it doesn't show an ordinal here. And then ordinal 1 is the void func entry point. So let's pop over to the void func one and see what's going on here. So you can see looks like they create a mutex. And then interestingly enough, it looks like they start 2 threads here. So this is the first thread that's being started, and this is the second thread that's being started. So let's just rename those thread 1 and thread 2. Thread 1, and name that thread 2. And then you can see that there isn't much else to the program here. One thing that I do want to point out is they do have the wait for single object, where they're pushing the object handle, ESI. And this is something that you'd have to look up on MSDN, but you can see the return from begin thread EX is the handle to the thread, and that's being returned in EAX. That's just the standard call, Windows 32 API standard call. So the handle is being returned in EAX. They move it to ESI, and then ESI is what's pushed on to the stack as the handle for wait for single object. So what's important here is we are only waiting for the second thread to finish, and then the program terminates. So if that first thread takes longer than the second thread to run, it's not going to be run. The program's going to exit before that thread can finish running. So when I first looked at this was the first thing I thought was, hey, maybe thread 2 is completing its task before thread 1 and exiting the program, and thread 1 is where all the interesting stuff is. So let's just dive in here. We'll dive into thread 2 first. It looks like this function is mostly, and again, I'm going through this super quick. I'm only looking at the Windows 32 API calls, and really what I'm looking for is any calls to like stuff that would generate network traffic. Since I know that this is probably a downloader, and I know that the downloader functionality is not working in the sandbox. So what I'm going to do is I'm going to pop back to the main, and I'm going to dive into thread 1 and see what's going on. What's going on in thread 1. So let's pop over here, go into thread 1, and in thread 1 we've got some more mutex stuff going on. Oh, get, that looks pretty good for network traffic, right? Get string, make some calls into here. What's going on here? Any API calls? I'm just looking right now. I'm just doing a quick surf for API calls, just trying to see last.so. Maybe that's what it's downloading. Again, I'm just looking really quickly to see if I can see any API calls to figure out if this. Oh yeah, here we go. Here's our network traffic. Internet open, internet connect. All right. So HTTP open request. Okay. So again, I don't know what these functions do. I have no idea. All I know is in the thread 2 that we just looked at, I saw API calls to work with the registry, and in thread 1 here, I see API calls for network traffic. So remember what I was saying if one of the threads if the second thread exits before the first one will not complete its tasks, right? It's going to kill the process. So why don't we pop back into main, and here we go. So we're going to rename this thread 1 network, and we're going to name this as registry. Okay, so again, this thread with the registry stuff is the only thread. Its handle is returned in EX, passed to ESI. ESI is passed into wait for single object. So this entire program is only waiting for the registry thread to complete. And once that completes, program's over. Whatever's going on in the network thread, it's not going to happen. So what I suspect is happening is this registry stuff is taking not very long, and it's exiting. Maybe there's an error. Maybe it doesn't have privileges to write to the registry, something like that. And it's just exiting. And this network thread doesn't ever have a chance in the sandbox to actually execute. Now, since my buddy just wanted to be able to run this in a sandbox, and get the network traffic out of it, we have a very simple thing to do here. So instead of having to reverse engineer what's in the thread and kind of pull out the URL, you could already kind of see that you can see the strings are not obfuscated or encrypted. So you could probably just do it really quickly with IDA. But the whole point of this tutorial, again, was not to talk about what's going on in the DLL. It was just to show you how to patch stuff with IDA. That's it. So the first thing you need to do is to turn on the opcode listing. So if we go into options, general, and then number of opcodes, let's just set that to 8 so we can see 8 opcodes. And you'll see what this does is this shows you the actual opcodes that are being interpreted as the assembly, or that are being shown as assembly code, readable assembly code. These are the actual hex opcodes that are the assembly, basically. So we can basically see what these are. And the reason why we're doing this is because we want to see the call to create the thread for the network, and we want to see all this extra stuff in here is being used to create the second thread for the registry. So we want to just null that stuff out. And then what we'll have is the return from the network thread. The handle to it will be an EAX, and then that'll be passed into ESI, and then the wait for single object will actually wait for our network thread instead of the registry thread. And then we can run in the sandbox and it should work fine. So basically what we want to do is we want to, in a hex editor, we want to find all these bytes here. So all the stuff after we start our first thread till right when we create the second thread, we just want to null all this stuff out. And then the second thread won't be created, and it won't terminate the program before the first thread can complete. The way we do this is you basically find these bytes in a hex editor, replace them with NOP instructions, which is like 90 hex, but I'll show you how you figure that out in a second, and then save the binary, open it up in IDA again just to make sure that we've NOPed it out correctly, and then run it. And that's basically all there is to patching it. So the next step is to open our binary file in a hex editor and actually find the bytes that we want to replace and replace them with the NOPs. Let's just grab our hex editor here. So I'm using Synalyze, which is a OS X hex editor. You can use any hex editor that allows you to edit the hex bytes. So there's plenty of good ones for Windows that are free, some paid ones as well. For OS X, I like Synalyze. I do pay for it, but I believe there's a free version of it as well. So anyway, that's what I'm going to be using. But anything I'll do, you'll see all you're doing is replacing a bunch of hex bytes. So let's open up our test.dll. And the cool thing, cancel that. The cool thing about this hex editor is we can actually search for bytes. So what I'm going to do is I'm going to search for bytes here. This is used to push the offset to the thread, the registry related thread function. So this is going to be a little bit different in your hex editor because basically this is like the interface for Synalyze. But whatever hex editor you use, one of the criteria for me at least is that it has to have a search capability, a binary search capability. Otherwise, it's not really useful. It's just displaying the hex bytes. What to do? You need to be able to search in there. And so what I'm doing now is I'm searching for the push of the address to the registry thread that's being started. So 6890240010, and it looks like that's at offset 1A3A. Okay, so I found it here. This is the offset in the binary, and we can see the following bytes: 6A00, 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 right, twice. Then we have E8AF12, E8AF12. So we found the right place in the binary. And when you saw when I was doing that search, there was only one match for it anyway. So we know we found the right one. Now we want to actually backtrack a little bit because remember I said we want to NOP out or null out all of the stuff after the first call to the network thread to start the network thread right until after the second thread is started. So we just want to basically remove all the code related to starting that second thread. So if we pop back over to our hex editor, so we can see That's 6A, 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 6A. Oh, there's too many 6As. 3 6As. 6A. Yeah, there we go. So basically it looks like all of this stuff up until E8, up until 8BF0. So let's see, where's that? 8BF0. Not including ABF0, sorry. So basically all of that needs to be null bytes. And then basically we will have killed that entire function here. So before we do that, I just want to point out, if you don't know how to find out what a null byte is in hex, you can go to any x86 architecture instruction set and they will provide you. So if we go back here, we can see all of the instructions here. And then if you click on one of the instructions, so I just clicked on NOP there, which is no operation, stands for no operation. You get the mnemonic, and then you have the actual opcode, which is the hex byte that it showed that you need to use to instantiate that mnemonic. So for us, it's 90. So basically, or 90 hex. So basically, what we're going to do is we are going to replace all of those bytes in our hex editor, all of these bytes here, with 90 hex. So the way it works in my hex editor is you can actually just type in 90. You see, I've replaced it. So I'm just going to copy in a whole bunch of 90s. All right, and there's our 8BF0. Let's just pop back over to our IDA instance to make sure 8BF0 is correct. So what we want to do now that we've patched our file is we just want to save it as a new file. So patched or something like that. Patch.dll. And then let's open a new instance of IDA and make sure that all those bytes are patched out. Okay, let's just open that file that we saved. Taking a minute to analyze it. Let's go to the exports, go into the void function, and here we can see we've knocked out all of the code after our begin thread. And if we want to just quickly compare that with the original, here's the original, we can see that we actually removed all of that code there. So here was the here's the EAX to ESI, then move EAX ESI, and here we still have the move EAX or ESI. So there we go. We've basically patched out this this binary, and now it should run in the sandbox. So let's give it a try. So back to our good old friend payload security. Here I've loaded up testpatch.dll. Let's put in their little CAPTCHA stuff here. What does that look like to you guys? PEMEXDEPTOS. Looks good to me. Nothing standard. Sure, let's share it out and I consent. All right. So this is going to take a while, and through the magic of time lapse, when you come back, it'll be done. Hey, I should have snapped, and then it'll be done. And with that, it's analyzed and done. So let's go down and take a look and see what happened. So we can see there's a silly error that I don't think it really means too much, because if we look down here, we can see that it actually got some network traffic out of it. So here's the domain that it tried to contact. That's the IP that it resolved to. I don't think we're going to get any HTTP traffic, no, because I think that host has been taken down. This was an old sample from a while back, so it's probably the C2 isn't active anymore. But at least we got the network traffic, so you can see that the network thread was able to complete without being killed, because the registry thread completed before it and killed the program. So since we got rid of the registry thread, we knopped it out. The network thread was able to complete, and here we have the network traffic in the sandbox. So hopefully you enjoyed that. Just a quick intro how to patch a binary, finding the opcodes in IDA, and then patching them out in a hex editor. Hopefully that's useful. I have a few more of these sort of shorter videos just focusing on one small technique or tip. I've had quite a few requests for that, and I know Sean has as well. So we'll try and answer those. And on that note, if you have any requests for a sample you'd like to see us analyze, or a analysis technique or a tool that you want us to show, to sort of walk through or describe in detail, give you some information on, please do hit us up. Our Twitter links are in the description of the video below. So hit us up on Twitter. Our DMs are open. You don't have to ask for a follow or whatever, or leave a comment below the video. Also, the sample, the original sample and the patch sample, as well as any tools I used, are also going to be linked below in the video, below the video. And I think I'm going to put up a small descriptive post on this as well that'll be linked. So just look for all that below the video. So like I said, hopefully we can get more of these videos out. I know there's some pretty cool ones that Sean's been working on, so hopefully we can get those out to you. So with that, keep exposing the mechanics behind the malware and stay curious.